by Dr. Sathish Govindarajan. He is an associate professor in our department, and his research interests are in combinatorial geometry, algorithms, and computational geometry. So.
Okay, good afternoon to you all. So last row, can you
settle
hear me?
down fast, please.
Am I audible to the last row? Okay. Okay, so what I want to talk to you about and expose you towards is an interesting area called as geometric graphs. And so I'll try to sort of scratch the surface of it and try to give you a exposure towards it. So, so again, I want this talk to be very interactive. So just feel free to interrupt me if something is not clear. If you have some comments or some questions, just feel free to interrupt me. So you have seen from the title the two words probably in separate contexts. You might have seen graphs, you might have had a course in discrete structures, discrete mathematics, or maybe even graph theory, and you might have seen the word geometry even from your high school. So this thing is sort of a nice combination of both these topics, geometry and graphs. So let's first broadly say what geometric graphs are in a very abstract sense, and then we'll go into particular instances. So as you know, what is a graph? Can someone quickly say what a graph is? You have a set of vertices and some edges connecting the vertices, right? So in the case of geometric graphs, the set of vertices actually typically represent a set of geometric objects. Right? V is usually the notation used for vertices. And you have an edge between two vertices or between two geometric objects based on some geometric condition. For example, if the objects intersect, then you will put an edge. Right? So this is very broadly the notion of geometric graphs. It's called geometric graphs because what you have is a graph, but the graph is coming from some geometric setting and some geometric properties. And on these geometric graphs, you would like to ask the standard set of problems which you generally ask on graphs, which includes things like, how do I color this graph? How do I find a clique or an independent set in this graph? So are these terms like independent set, coloring, clique familiar with all of you? Is anyone who is not clear about these terms? Okay. So if later you have something, you can I can quickly go over it. And there are two types of questions one can ask. One is more structural questions or combinatorial questions. It's like saying that if certain properties are met, then certain statements will be true. For example, you all know that for planar graphs, you can color it with 4 colors, right? This is called as this is a structural property about planar graphs, or a combinatorial property of planar graphs. And typically, you would either like to get some bounds or characterize the structure of such graphs. That's the first type of questions which people typically ask. And the other questions is computational questions or algorithmic questions, which typically include come up with an algorithm to compute the best possible parameter, whether it's the independent set, coloring, clique, whatever it is. You want an efficient algorithm, and sometimes you might not be able to find an efficient algorithm. Certain problems are called inherently hard. I don't know if you have already seen things like NP and so on. If you have not seen, you will probably seen soon. Then for such things, you might want to come up with some approximation algorithms. So these are the types of questions which typically people ask on graphs in general, and particularly you can ask them on geometry graphs also. Okay. So I broadly define geometry graphs, but there are a huge variety of specific geometric graphs one can define, and it's beyond the scope of the lecture to go through all these types of geometry graphs. But what I will do is I will try to categorize these geometric graphs based on some broad classes, and typically they will be dependent on how you define the edges. As I told you, vertices are representing geometric objects, and edges will depend on some geometric condition on these objects, right? So depending on what is that edge conditions, you could have a class of geometric graphs called as intersection graphs, and as the name says, you will put an edge between two objects if they intersect. These are naturally called as geometric intersection graphs. There's another class of graphs called as proximity graphs, and edges are put based on certain proximity conditions. I'll keep it vague as of now, and later when I talk about it, you will see what proximity means. And the third general class is edges are put based on some distance conditions. So what I will do in this talk is I will spend most of my time on the first class of graphs, intersection graphs, and time permitting, I'll give you an idea about the second class. So this is what I plan to do in the lecture. So any questions before I move on? Okay, good. So let's take a classical example from the first class of graphs, which is the intersection graphs. Okay. And this specific example I'm taking is called as an interval graph. How many of you have seen or heard of interval graphs before? Anyone? One. Okay, good. So most of you have not, so I was planning to spend a good amount of time here, so that's good. Most of you have not heard it. So what is this graph? The objects are intervals. Intervals denoted by a pair of coordinates a comma b. Right? Intervals on the real line. So these are the objects, and I will put an edge between two intervals if they intersect. As the name says, intersection graphs, right? So for example, if you see here, so I have drawn the intervals there one above the other, but they actually are lying on the real line. So just for ease of illustration, I have drawn the intervals one above the other. So if you see here, we have 7 intervals or 6 intervals, and below is the interval graph of those intervals. There's an edge between A and D because A and D intersects. There's an edge between A and F because A and F intersects. So you can verify that the graph below is actually the intersection graph or the interval graph of the intervals shown in the figure. Is the definition of interval graphs clear before we proceed? If something is not clear, just feel free to clarify it, because I'm going to be talking about some properties of interval graphs from now on. Any questions? So just feel free to ask questions. If something is not clear, just feel free to ask. Everyone will benefit. Yeah?
If on the number line one, like the object comes exactly after object A, will that be considered an intersection? Like A ranges from 1 to 4 and B ranges from 4 to 6.
Yeah. So the question is, if the intervals are just touching each other at the end point, would you consider it an intersection? And depends on the motivation. Typically, it's considered as an intersection because the intervals are considered closed, which means that 4 is part of it. But sometimes people don't consider it as an intersection too, right? So as far as our presentation goes, I don't think I have examples like that, but let's say that actually it makes things simpler. We don't consider them as an intersection. If they just touch at the end point, for the purpose of this talk, we will not consider them as intersecting. It's intersecting only if the interior of the intervals intersect. But people could also define it other ways around. So there are things known as weighted graphs, and typically it makes sense to put the weights on the vertices. Maybe the intervals have some weights and you can put weights on the vertices. Edges also is possible, but it's not natural. So what do you mean by putting a weight on an edge? Maybe how much it intersects, 50% or so on and so forth. True. But as far as the talk goes, we will be worried about no weights. At some point, the intervals will have weights, but not the edges. Okay, good. Any other questions? Okay, sounds good. So this is a class of graphs. The interval graphs have been studied for quite some time, at least for about 40-50 years or so. And it's got applications in broad domains. I've just listed 2 or 3 of these domains: operations research, computational biology, mobile networks, but its applications are more widespread. If you just do a Google search, you will be able to see where are the places where interval graphs can come in. So my talk will not go into specifically applications, but I would be exploring various theoretical properties. Okay. So to motivate interval graphs, I am going to give a problem. This is called as the consultant problem, and it will be clear what is the connection between the consultant problem and interval graphs. The problem is the following. So think that you are a consultant or an expert in some field, and various companies would like to get your would like to consult with you on various problems they have. And the way this works is that the company A will say that I want you to come to my company and consult for us between this particular time interval. So I want you to come from 6 to 12 today to consult on a particular project of mine. So multiple companies which are sort of contacting you saying that we would like your consultancy, but they say that this is the time interval we want you to come. So there are, let's say, 7 companies, each giving you a time, a start time to an end time. So what is a natural problem? You would like to take as many jobs as possible, but you can't take all the jobs, right? Because if, for example, the first job and the second job you can't take simultaneously. You're just one person. So there are certain jobs which cannot be taken simultaneously. Under this constraint, you would like to take the maximum number of jobs possible. Is the problem definition clear? Okay. So you have to choose the maximum number of jobs, and the job should obviously be non-conflicting. So here, let me sort of clarify that the point which was asked earlier. So if two jobs are coinciding at an endpoint, let's say for the job 11:15 and 15:18, I don't consider them as conflicting. I can take up 11 to 15 job as well as 15 to 18. So the problem here is to come up with an algorithm to find the maximum number of jobs you can take. So keep in mind the problem. We will come back to solving the problem later. So in this case, it's clear. I mean, you can take at most 3 jobs. This is one of the solutions. Maybe there are other solutions. The solution need not be unique. But in general, when you have millions of jobs, that's when you need an algorithm which works even when the number of input is large, right? So keep the problem in mind. Think about the solution. We'll come back to it later. But what is the connection between this consultant problem and interval graphs? Can we model this problem as interval graphs? How do we model it? Pardon? So you have to build a graph. What is the graph you want to build? It is the interval graph where the intervals are nothing but the start and end time of each job. So each job is an interval on the real line, and you build an interval graph on that. Now what is the problem corresponding to? The fact that you want to choose the maximum number of jobs. What does it correspond to in the interval graph? Longest path. So this is actually corresponding to something called as a maximum independent set, right? So what is an independent set? Can someone define what an independent set is? Pardon? What is an independent set? It's a subset of vertices with the property that there is no edge between any two vertices in that collection. Might have, might not have. Doesn't matter. So, independent set is a subset of vertices with the property that if you take any two vertices in that subset, there is no direct edge connecting them. They are independent. And with this definition, is it clear why this problem of finding the maximum number of jobs corresponds to finding the maximum independent set? Is it clear? No. Okay. So I'll define one more problem which is also relevant to interval graphs. It's a classroom allocation problem. Again, in your university or in IISc, let's say that you have a number of classes which happen in a day. And these are classes of different lengths of time. Right? So there are 7 classes. Each class is denoted by when the class starts and when the class ends. Right? Now what's the problem? I want to hold these classes in a classroom. And the question is, how many classrooms are needed to hold all these classes? Right? So what's the trivial answer? I mean, if I ask you to say how many classrooms are needed, right, I can give one classroom to each class and there's no problem at all. So what is the natural question which is not at all clear? You want to find the minimum number of classrooms which are needed to hold these classes. Right? So decide how many classrooms, meaning minimum number of classrooms are required for holding these classes. Is the question clear? Any clarifications on the problem? And again, it's clear that certain classes cannot be held in the same room. For example, the first and second class cannot be held in the same room, right? First class is from 6 to 12, the second one is from 8 to 10, right? Again, what is the connection between this problem and interval graphs? Again, you can think of each class as an interval on the real line, depending on what time it starts and what time it ends. Now, what does the finding the minimum number of classrooms correspond to in the interval graph? Number of independent sets. I mean, what do you mean by number of independent sets? Okay, so there is something called as coloring a graph. Can you think about solving this or modeling this problem as coloring the interval graph? And what do I do with that? And that would correspond to? Yes. I don't think that will correspond to the minimum number of classrooms. So think about it. The complement could be a very dense graph, and the components don't really have to correspond to number of classrooms. So let's try to come back and think of it as coloring the graph. So what do I mean by coloring a graph? Color what? Correct. So let's, in terms of graph terminology, you want to color the vertices of the graph with colors such that whenever there is an edge between two vertices, they cannot get the same color. They have to have different colors. So this is called as coloring a graph. Typically they call it as vertex coloring of a graph. Again, the property is color vertices of the graph with some colors, with the property that whenever two vertices have an edge, they must get different colors. Now, what is this problem? Now, in terms of this coloring, what is the minimum number of colors required to color this graph? And this is called as a chromatic number of a graph. It's a very well-studied parameter and a well-studied problem in graph theory. Given a graph, what is the minimum number of colors required to color this graph, which is also called as a chromatic number of the graph. So the problem is nothing but finding the chromatic number or the minimum coloring in the interval graph. Again, think about how you will solve this problem. We'll come back to the solutions in a minute. Okay, so is the two problems clear? The classroom allocation problem as well as the scheduling problem, the consultant problem? Any questions? Yes. Yes. So we'll come back to it. But let me rephrase the question in a different way. Are the problems which I stated, whether it's the classroom, let's take the classroom allocation problem, right? The question, what is the minimum number of classrooms needed to hold the classes, and finding the minimum coloring in the interval graph, are these problems equivalent or not? Or do you think one is harder than the other? What I'm asking is this question and this question the same or different? So there's someone saying same.
Anyhow, you are framing that question with respect to this question. But if we are having a solution for this question, then we can obviously use that and solve that question.
Correct. If I have a solution to this problem, finding the minimum coloring, then I can use that and solve this. Is the other way also true? If I have a solution somehow to find the minimum number of classrooms, then I can find the coloring of the interval graph. Is that also possible? That's what I mean by equivalent. His question was that maybe this is an easy problem, but you are converting it into minimum coloring, and maybe that is a hard problem and you are losing out on it. Maybe you can directly solve it in polynomial time. I guess that's the question. So the question I am asking is are the problems equivalent, or this is harder than the other? Right. Okay. So I will let you think about it. I'm going to give you a lot of exercises throughout this lecture. Think whether they are equivalent or not. Okay? Okay. So sounds fine. So we have two problems. We'll come back to the two problems. But I want to sort of now slightly change the flavor of the question into something more structural. These are all algorithmic questions. You want to design an algorithm to solve these problems. Right? Now I'm going to move to a more structural question on interval graphs, and then we'll come back and solve this. Right? Okay. So forget about consultant, forget about classroom problem as of now. I have a set of intervals on the real line, and suppose I tell you that among the collection of intervals which I have, every pair of intervals intersect. This is a special property which my intervals satisfy. I am telling you as part of the input. And I want to prove or claim that if this property is true for the set of input intervals, that every pair of intervals will intersect. I want to claim that all the intervals will have a common intersection. And obviously, when I say I want to claim this, I would like to give a proof for the statement. Is the statement clear? What is the input and what you want to prove? It might seem like a natural statement, but the proof is not at all trivial. That's why I have sort of put it as part of the lecture. How do you prove this claim? When I say I want a proof, I want a mathematical proof. It's not enough to take intervals, try to sort of simulate it on your computer and see that whether this is true or not. So I want a mathematical proof. How would you prove this statement? So again, you might have seen notions of mathematical proofs in your classes on discrete structures or even graph theory. Yes? But what do I want to prove? I want to prove that all the intervals have a common intersection. How is that conclusion derivable from the observations you are making? The observations you are making is correct. If I try to make an interval graph, it will be a clique, there will be all edges. So if I color it, I will require n colors if there are n vertices. All that is valid observations, but I don't see how to sort of use those observations to prove this. So forget about interval graphs for the moment. Let's try to think of them as just intervals. I want to prove that all the intervals have a common intersection. No, so when I say all the intervals have a common intersection, what I mean is, so if I see this example, right? For example, let's say this particular point on the real line is present in every interval. The intervals, if I take the intersection of the intervals, it's a non-empty set. That's what I mean by this statement, all the intervals have a common intersection. Right? So what are the ways of proving things which you have seen? I mean, there are some natural or standard techniques which people use for proving things. Induction is one natural thing. What else? Contradiction is one way. Right? So I will leave it as an exercise for you to prove it by induction. I am going to prove it not by induction. You can also prove it by induction, but do it as an exercise after your lectures today. I want to prove it in a more constructive manner in the sense that I would like to find one point on the real line and show that that particular point is present in all the intervals. And if I am able to show that, I have proved what I wanted to prove. Right? Because there is a point which is present in all the intervals, which means that there is a common intersection. And that's my goal. Given the intervals, somehow I want to sort of define this red point on the real line and prove that that point is present in all the intervals. If I do that, I am done. I have proved it. Now, how do I find this red point is the question. That's the crucial thing left in the proof. Pardon? In the intersection. And that's circular, right? I mean, that's how I want to prove that there is an intersection by finding this point. I mean, suppose I give you the bunch of intervals and I tell you that every pair of intervals or every two intervals in my collection intersect. I want to use that fact to somehow define this point, red point. But that's what I want to prove, right? That's my final thing I want to prove. I am proving that using this idea. But how can I use that? Right? That's circular logic. Okay, so in the interest of time, I will sort of tell you. You define this point as the end point of an interval, the right end point of an interval, which is leftmost. Or in other words, you can say, look at the interval which ends the first and take its ending point. Suppose I define that as my point P. Right? Now I want to basically claim that this point which I have defined actually is contained in all the intervals. Is it clear how I have defined the point P and what I have to prove? I have defined the point as the end point, the right end point, which is the leftmost, which is exactly this point. And I want to claim that all the intervals will contain this point. How do I prove that?
An interval does not contain P. It should start later than this ends.
So you want to prove it by contradiction, right? So what is the argument? Suppose the point P is here. Yes, this is the red interval. I am drawing it in blue. Suppose there exists an interval which does not contain P. Then
it should start after P.
It should start after P. Okay.
But there will be no there will be no intersection between the red line and this particular, which will be contradictory.
Okay. So what what she's saying is that this is the red point. Okay, let me use the red marker so that it's very clear. This is the red point, and this is the interval which is defining the red point. Suppose there is an interval which does not contain this. She's saying it must start after this. So let's say there is an interval like this. But then if there are two intervals like this, there is a contradiction. Why is it a contradiction? Correct. I said that every two intervals will intersect and these two are not intersecting. There is a contradiction. Is the proof complete? Right? So the proof is only partially complete because it might happen that an interval is not containing this point because it is ending before. Then there is again a contradiction. P was defined as the right end point which is leftmost. But then if this was there, then I should have chosen this. So there is again a contradiction. That completes the argument. That there cannot be any interval which does not contain P, which means that all the intervals will contain P, which means all the intervals will have a common intersection, QED. Okay, so this is sort of a structural property for which you have to give a theoretical proof, a sort of mathematical proof. And that's exactly what I did. There are two possibilities of the red point not being contained. Either the interval is completely to the left of the red point or to the right. In both cases you have contradictions. Is the proof clear? Any questions? Yes. Pardon? The conclusion of the proof is that I wanted to prove the statement. I wanted to prove that all the intervals have a common intersection. And I have proved that because I showed that there is a point, the red point, which is present in all the intervals, which means that all the intervals contains that point, which means that all the intervals must have a common intersection. Common intersection means that there has to be at least one point, right? The intersection is non-empty. Okay, so this has nothing to do in terms of graphs, in terms of interval graphs. This is a property about intersection of intervals. Right? This is a structural property about a collection of intervals. It's not anything about interval graphs per se. Fine. Okay. So, why I said that is because there is a very important and classical theorem which actually is an extension or a generalization of what we proved. It's called as Helly's theorem. It says that if you have a collection of convex objects, if you don't know what convex objects means, don't worry. Think of the objects as circles, ellipses, rectangles. All these are specific types of convex objects. Think of them as your favorite geometric object. And the statement of this theorem is that if in this collection, if you take any d plus 1 objects, these are objects lying in d dimensions. If you take any d plus 1 objects and if they have a common intersection, then all the objects have a common intersection. Now, what we actually proved is this theorem for d equal to 1. For d equal to 1, the convex objects are nothing but intervals. And we said that if every two intervals have a common intersection, then all the intervals have a common intersection. That's exactly what we proved now. And this statement says that this is true for any dimension d, for convex objects. And one quick thing to note is that this statement which we proved for intervals actually could be misinterpreted that it might be true for other objects too. For example, this statement which we proved, right? If instead of intervals, if I replace them by circles, is the statement true? I have a collection of circles lying on the plane, let's say the blackboard, whiteboard. Every pair of circles intersect. Then can I claim that all the circles have a common intersection? You can't, right? So if you say you can't, you have to tell me why. That theorem might say something, right? So whenever you say some statement is false, you have to give a counter example, right? So I will leave it as an exercise for you. You can easily construct circles such that every two circles intersect, but all of them don't have a common intersection. How about rectangles? If I take, instead of intervals, if I put rectangles, is the statement true? I have a bunch of rectangles on the whiteboard. Every pair of rectangles intersect, and let's say rectangles are axis parallel rectangles, the ones which you are most familiar with. The rectangles are having vertical and horizontal sides, right? I have a collection of rectangles which are axis parallel, vertical and horizontal sides. Every two rectangles intersect. Can I claim that all the rectangles will intersect? Again, if you say no, you have to come up with a counter example. So let me spoil the answer and say this statement is true. For rectangles, the statement is true. Of course, when I say it's true, I have the obligation of giving a proof, right? So the question exercise for you is to prove for rectangles. This statement is true for rectangles, but false for circles. Okay. So in general, for convex objects in d dimensions, you require this d plus 1. And the proof for this theorem is actually for d equal to 1 we did, but for general dimensions is actually quite complicated. And interestingly, there are multiple approaches or multiple proofs known for it using different techniques. At least there are 5 different things. And there is also a proof which is generalizing what we did for intervals to higher dimensions. So if someone is interested, you can contact me. I can point you to the right paper if you are interested in reading that. Okay, so let me step back and come back to the problems we posed, right? So again, exercise problems don't discuss amongst yourself now. These are exercises. Note it down and think about it later. And you're free to drop by and discuss it with me. My office room is 236. So typically in the afternoons I'm available. You can drop by and discuss the exercise problems. So don't discuss or distract yourself and others with the exercise problems. Let's come back to the 2 problems which we defined. Right? One was the consultant problem. Now I want a method to solve this problem. Is this problem solvable at all in polynomial time, as he said? If it's yes, you have to give me an algorithm. Pardon? So you want to come up with a greedy algorithm. Sorry? Pardon? Okay. And? No. So let's say I take the interval which ends first, then? Okay. 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 So you gave me a greedy strategy, right? And note that greedy strategies could be quite different. There is no one greedy strategy. You could have taken that interval which is the smallest, right? That's also a natural greedy strategy. Or you could have taken that interval which conflicts with the least number of other intervals. That's also a greedy strategy, right? So the important thing about greedy strategies is to show that your strategy works. Right? So why is the strategy which you mentioned giving you the optimal answer? Meaning, why will it return the maximum number of jobs? I mean, that's still vague, right? I could have said take the job which conflicts with the minimum number of other jobs, so that when I pick this, I will be only throwing away minimum number of other jobs and then recurse. Or I can say pick the job which has the smallest interval so that I will leave the maximum amount of time left for me to choose. So I can intuitively give a reason for each of the strategies I defined, and seems very natural. And it turns out that the strategy which he said actually works, whereas the two other strategies which I said will not work. You can come up with a counter example, but maybe there's a counter example for his too, right? I don't know. The only way to verify that is to give a proof. How do you prove that this particular greedy strategy he suggested will give the maximum number of jobs? How do you prove that? Yeah. Yeah.
So you select the job which gives the maximum time. You said you give the maximum time, but till that time you can only select one job.
Yes.
You select the job which gives the maximum.
Sort of intuitively, what you are saying is correct, that if this is the job which ends first, all the other jobs are ending further. At this point, you can only select one job, and you have selected one. And then you have to basically, let's say that the next job is here, which is finishing first. At this point of time, you can only select two jobs. I mean, not you can select. The best possible thing, algorithm can choose only two jobs, and you have done that. So you have to argue that at every point. And at the end, you have to say something. Right? So again, that's the high-level idea of a proof, but you have to sort of work out the details of how you actually have to prove it. Whenever you design a greedy algorithm, it's very, very important that you give a mathematical proof that it is correct. Otherwise, you can be very well wrong. In fact, most natural greedy strategies will not work. Okay, so I will sort of leave that, working out the mathematical proof with all the details and exercise, but the intuitive idea given is more or less the idea of the mathematical proof. Now let me sort of ask an extension question. Suppose the jobs are not identical. Each job is giving you a different profit. They give you a salary for being consultant, and the salary might be different for different jobs. And what is your objective now? You don't care about how many jobs you do, you only care about what is the total revenue you get. I can do just one job, but if it gives me much more revenue, then why do I care about doing many jobs? So the objective is to maximize the total revenue from the jobs. Now this is a slightly different problem. Will the previous algorithm work? The previous algorithm will not work. You can easily convince yourself. You can come up with a counter example also. So what do I do now?
One approach maybe is just try to select the job which has the maximum profit associated with it, or the second approach you can try just increasing your number of jobs done. So something related to knapsack profit.
Yeah. So interestingly, for this particular question, there is no known greedy algorithms. And most likely there is no greedy algorithm which will solve this problem. So greedy algorithms will fail in this problem. Whichever natural greedy algorithm you can think, people have thought about it. There are counter examples which people have also found. So what do I do? greedy algorithm is out of the picture. You can't choose the job with the maximum profit or by any other criteria choose jobs. What do I do? Correct, but how do I solve that problem? So there is another nice, very powerful technique which you might have seen or might have even been exposed to in your algorithms course, dynamic programming. How many of you have not seen dynamic programming so far? All of you have seen dynamic programming? Okay. So the exercise is solve this problem by dynamic programming. Okay? Another question, again an extension question. Suppose instead of one consultant, there are k of you, let's say 10 of you, and you are given a bunch of jobs, and you might want to maximize the total number of jobs amongst you in total, or you might have a profit for the job and you want to maximize the maximum profit. The difference here is we have looked at the problem for k equal to 1, but if k is some integer greater than 1, how do you solve the problem? Is the problem clear? So these are all extensions of the question which I initially posed, and think about how to solve them, and you can sort of discuss the solution to me at a later point. Okay. Let's quickly come to the other question, classroom allocation. Now how do I solve this problem? So please don't discuss amongst yourself. You have plenty of time after the lectures to discuss and solve these things. So how do I solve the classroom problem? What is the classroom problem? I want to find the minimum number of classrooms required to hold all the classes. How do I solve it? Yeah? Maximum number of collisions. New? New? Stat meaning? No. My objective is to assign a classroom to each interval, right? I have to tell which classroom to hold each class in, and I want to minimize the number of classrooms I require for this problem. Yes? What is the depth? Yes? So one thing he has observed that he said depth of the set of classes, meaning at any particular point of time, what is the maximum number of classes which will be happening at that point? That's called as a depth, let's say. Let's define that. Now, why is that definition helpful? It's helpful because the number of classrooms required is at least this much. I cannot have fewer classrooms. Suppose the depth is 5. I need at least 5 classrooms, because there are 5 classrooms happening at, let's say, 11 o'clock. But what is not clear is, can I always have 5 classrooms and allocate it to all the classes? If I can do it, then that's great. Right? What is not clear is, how do I decide, how do I use only the depth number of classrooms and make sure that all the classes are held? Or in other words, in the interval graph notation, if I can use the depth number of colors to color this interval graph, then I have solved my problem. Why? Because I cannot find fewer number of classrooms. And Again, the way to solve this problem is a greedy algorithm, and I will tell you what the idea is, which is very natural. What is an exercise for you is to prove the correctness. You just, whenever, let's say you sort the intervals by the starting time, and whenever a class starts, assign a classroom to it. If there is no classroom, allocate a new classroom, right? And whenever a class ends, that classroom is made free, so that some other classes can use it. So at any point you see that existing classrooms, if they can accommodate this class, go ahead and allocate it. If not, you use a new classroom, and keep doing this for every class, sorted in the increasing order of start times. Again, a very natural greedy strategy, but what is not clear is to give a proof of correctness. Why will it work correctly? So I'll leave that as an exercise. Okay, so I have about 5 minutes. Okay. So what I have done basically so far is looked at interval graphs, or a collection of intervals, and looked at problems which either could be algorithmic in nature, which was the consultant problem and the classroom problem, or it could be structural in nature, where you have to prove certain statements. We proved that all of them will have a common intersection, right? So it could be a structural question which you have to prove, or an algorithm you have to design. And we saw that on the case of intervals. Now what I want to say quickly, just give you a feel of, is the other class of graphs, proximity graphs. So there is a very classical graph, or an important graph, called as Delaunay graph, or Delaunay triangulation. And this is, I'm going to use this as an example of proximity graph. What is this graph? You are given a set of points, n points let's say, and the vertices of the graph are nothing but the points. I will put an edge between 2 points if I can find some circle passing through these 2 points but does not contain any other point in my point set. I have put an edge between this point and this point because I have this particular circle which is passing through both these points but does not contain any other points in my input. Similarly, I have put an edge between these 2 points because I have the circle which is passing through both and does not contain any other point. Now if I try to see if I can put an edge between this point and this point, you can sort of intuitively see that I will never be able to find a circle which passes through this and this without containing any other point. So there is no edge there, right? So that's how the graph is defined. Whenever there is an edge, there has to be some circle passing through both of them which is empty. Empty means it doesn't contain any other point. And this is a very important graph. It's been applied in graphics, mesh generation, in vision, many other places. And it's also called as a Delaunay triangulation because the graph is composed of triangles. If you see this graph, you will see that whenever you take a point set, the graph will be consisting of triangles. That's why it's called as a Delaunay triangulation. Now, an interesting question is, this graph which I have defined, in fact, is a planar graph. I mean, that's how it looks also, right? Does everyone know what a planar graph is? What's a planar graph? A planar graph is a graph which can be drawn on the plane such that no two edges intersect at an interior point. The edges could be possibly touching each other. This edge and this edge is incident on the same vertex. That is not intersection. The edges should not intersect each other. If you can draw a graph on the plane without edges intersecting, such graph is called planar graph. Now this graph which I have defined turns out to be a planar graph. Now again, when I say it's a planar graph, again this is a property of the graph which I have to prove. Right? So think about how you will prove, or more clearly, think about a proof by contradiction. Suppose two edges are crossing in this graph, then there is a contradiction. Think about that. So why is this planarity important? Because the planarity also gives you additional properties. For example, the number of edges in a planar graph will be at most 3 times n minus 6. A planar graph cannot have n choose 2 edges. It can have only 3n minus 6 edges. And this is actually proved by something called as Euler's formula. I don't know if you have seen Euler's formula or not. If you have not, you can read it up. So it tells that the number of edges is small. Chromatic number. A planar graph will have a very small chromatic number. In fact, there is a theorem which says that if you have any planar graph, you can always color it with at most 4 colors. Whereas in general, a graph might require, what is the largest number of colors a graph might require for coloring? N, right? If you have a clique, you might require n colors. Whereas I am saying here that if you have a planar graph on n vertices, you can always color it with 4 colors. And that's a very, very important and difficult result, which was proved almost in the 1980s and 90s. People have been trying to prove it for 300 years or so, and only about 30 years or so this proof was done, and that too it's a very complicated proof. So I think with that I will stop. Again, I just scratched the surface. I spent most of my time on intervals and interval graphs, but I gave you a flavor of proximity graphs too. I gave you a lot of exercise. I strongly encourage you to work it out at the end, because you'll always learn things by working out exercises. And feel free to drop by and discuss the exercises or anything about the lecture at my office 236. Any questions? I can briefly answer them. Thank you.
No questions?
So if you have no questions, it either means that you have understood everything I have said or nothing I have said. I hope it's the former. So thank you again, and work out the exercises and feel free to discuss them with me. Thanks.
Thank you, sir, for the lecture.